Lewis structures and their partners, the line structures, are a good first approximation for showing the general shape and structure of a molecule. But they actually don't do a very good job of explaining what's really going on in the bonding. In order to understand that, you first have to understand atomic orbitals, which we've gone through. And then you need to understand that molecular orbitals, which form bonds, between atoms, are created by linear combinations of atomic orbitals. So if you have a firm understanding of what the atomic orbitals look like, you can use that understanding to create molecular orbitals. And this is generally known as LCAO-MO theory. Linear combination of atomic orbitals to create molecular orbitals. So when you form a bond between two hydrogens, for example, to make H2, you start with a 1s orbital on one of your hydrogens and a 1s orbital on the other hydrogen, called HA and HB. And each of those 1s orbitals has a single electron in it. And you know that since it's an s orbital, it's spherically symmetrical. Which is where the s comes from. Spherically symmetrical orbital, so it's uniformly distributed. It doesn't matter which direction you walk away from the nucleus at, you're going to see the same variation in the wave function. And you know that if you plot that wave function, psi versus r, it will be an exponential decay, and it will be the same in both directions. And on this 1s orbital, you also have the same thing, and you have the same graph where we plot psi versus r, and we see that distribution. To form the bond between the two hydrogens, what we're going to do is we're going to take psi 1sa plus psi 1sb, which will cause constructive overlap and create a bonding orbital. Bonding molecular orbital. And we're going to take the other linear combination, psi 1sa minus psi 1sb, which will cause destructive overlap. And result in an anti-bonding orbital. Where the definition of a bonding molecular orbital is lower energy than the atomic orbitals. Where it came from. And the definition of an anti-bonding orbital is higher energy than the atomic orbital that it came from. There are also, in some cases, non-bonding orbitals. Non-bonding orbitals have the same energy as the atomic orbitals that were created themselves. Non-bonding orbitals are pretty common in molecules that have lone pairs. There won't be a non-bonding orbital at H2 because we've only got two orbitals, and we're going to either interact with constructively or destructively. One of the rules of molecular orbital theory is that you have to have the same number of molecular orbitals as you had atomic orbitals. So in this case, since I'm starting with 2 atomic orbitals, 2 1s orbitals, I need to have 2 molecular orbitals. Another rule is that the total energy must be the same for the molecular orbitals as the atomic orbitals. That's called conservation of orbital energy. So if one of my interactions causes a drop in energy to create a bonding orbital, there must be an equal and opposite rise in energy to create an anti-bonding orbital, so that the sum of the 2 atomic orbital energies is equal to the sum of the 2 molecular orbital energies. And a third rule is only atomic orbitals with the same symmetry can overlap. You can't overlap a p orbital with an s orbital unless they're pointing at each other. Because if you overlap an s orbital with a p orbital, there would be constructive overlap here, but there would be destructive overlap here. So there'd be no net overlap possible for this p orbital that doesn't have cylindrical symmetry with respect to the bond axis versus the s orbital that does. If you want to overlap a p orbital and an s orbital, the only way to do that is to point it directly at the s orbital. So now they are both cylindrically symmetrical with respect to rotation around the bond axis, and you get constructive overlap here without the corresponding destructive overlap, or destructive overlap without the corresponding constructive overlap. So you can create 2 different situations. This situation you can't create because there's no net overlap at all. So those rules are unbreakable. Same number of molecular orbitals as the number of atomic orbitals. That always has to be true. The total energy of the orbitals has to be the same for the molecular orbitals as the atomic orbitals. Conservation of orbital energy. And only atomic orbitals with the same symmetry can overlap with each other to create molecular orbitals that haven't changed their symmetry. That's called conservation of orbital symmetry. You can't break the rules of conservation of orbital energy and conservation of orbital symmetry. Another rule, which is more of a guideline than a rule, is that atomic orbitals prefer to overlap with other atomic orbitals that have similar energy. So in this case, this would be very favorable because the 2 hydrogen 1s orbitals start out at exactly the same energy. And I'm plotting an orbital energy diagram with energy on the vertical axis. So what does constructive overlap look like? Well, constructive overlap on the graphical representation, as you bring the orbitals closer together, looks like this. You've got constructive overlap here where the sum of the 2 atomic orbitals is greater than its parts. So you'll end up with a wave function that looks something like that. Destructive overlap, on the other hand, side 1SA looks the same as it did, but now we flip side 1SB upside down. And over here, 1SA has the same positive value as 1SB has negative value. They will sum to 0. We call that a node. The resulting difference will look distant from the two nuclei where the value of the wave function is now equal to 0. And that's called a node. Where the value of the wave function is equal to 0, there's 0 probability of finding the electron at that particular distance between the two nuclei. The radial probability function, which is what we're looking at here when we show this kind of arbitrary boundary, runs as psi squared, not as psi. So when we square this, we're going to see kind of a deeper trough. It's going to have the same general shape. And when we square this one, both of them are going to be upright. But we'll have a node, and it'll go to 0. The one where we have the constructive overlap is a sigma orbital. And you know it's a sigma orbital because the destructive overlap is a sigma star, where the star tells us it's anti-bonding, and the sigma tells us that it is cylindrical symmetrical with respect to the bond axis. The sigma orbital drops in energy, the sigma star orbital rises in energy, and this one drops by the same amount that this one rises, so that the sum. You'll notice that while I was forming these orbitals, the electrons were sitting in a box somewhere on the other side of the door. I kicked them out of the rooms and come back when I'm finished creating my orbitals. Now I'm going to use the Aufbau principle to put those two electrons into the new molecular orbitals. The first one, with a spin plus 1/2, prefer to flip its spin to spin minus 1/2 because it's between the sigma star orbitals. So it will go in here with a reverse spin. We've lowered the net energy of the system by putting both of the electrons into the bonding orbital and leaving the anti-bonding orbital empty. The bond order can be calculated, the orbital energy diagram. And the bond order is equal to the number of bonding electrons, which in this case is 2, minus the number of antibonding electrons, which in this case is 0, divided by 2. Number of bonding electrons minus number of antibonding electrons divided by 2. In this case is 2 over 2. Bond order is equal to 1. And that tells us we have a single bond between the hydrogens, which is what we knew from Lewis theory anyway. What do these orbitals look like? Well, the sigma orbital is formed by a constructive overlap of two atomic orbitals that both are in phase. That causes a bulge in the middle. And we get an orbital that extends over both nuclei. So the electrons are able to interact with both nuclei simultaneously, and they have a relatively high probability of being between the nuclei where they can attract both of them. The sigma star orbital is caused by destructive overlap. Or destructive interference. And so what we end up doing is chopping out that middle part. So we introduce an asymmetry. We have a new node. And they no longer look, those two lobes, like they're symmetrical with respect to the nucleus. They're no longer spherically symmetrical. One of them now leans towards the left, the other one leans towards the right. If electrons in this antibonding orbital have a relatively low probability of being anywhere between the nuclei and a zero probability of being exactly between the nuclei, which means they're not very effective, right? They're actually trying to pull the molecule apart. You can model constructive overlap by simply taking two soft and squishy balls, like racquetballs or balloons or something, and pushing them together and watching them bulge. It's trickier to imagine destructive overlap. What you would need is a basketball and an anti-basketball, so as you push them together, they would disappear, they would annihilate each other. Those volumes would annihilate, and if you push them together all the way so the nuclei were overlapping, there'd be no orbital at all. They would completely destroy each other. That there's no physical model for it. If you can come up with an anti-balloon for me, I'll give you extra credit. So what we've done is we formed a new bond with a bonding orbital, which is filled, and an anti-bonding orbital, which is empty. If you were to do diatomic helium, diatomic helium would look not very different from diatomic hydrogen from a molecular orbital picture. The 1s orbital on one helium atom with a single 1s orbital on the other helium atom. And since the electrons are not allowed to be present while we're forming the molecular orbitals, it wouldn't matter that now each of those 1s orbitals that we start with have 2 electrons in them. We would still form sigma bonding from psi 1sa plus psi 1sb. We would still form sigma star from psi 1sa minus psi 1sb. The sum of sigma and sigma star would still be equal to the sum of the 2 1s orbitals, because conservation of orbital energy has to be maintained. In this case, there is only one orbital. They have the same symmetry, so conservation of orbital symmetry is automatic. But now when we come to fill them, the first electron goes there, the second electron pairs off in the sigma bonding orbital. The third electron can't, because we would break the Pauli exclusion principle if we put a third electron in there. Remember that the Pauli exclusion principle says that no 2 electrons may have identical values for all 4 quantum numbers. So spin 1/2 and spin minus 1/2, there is no third spin state. The third electron has to go in the sigma star orbital. The fourth electron also goes in the sigma star orbital. You'll notice our bond order is now equal to 2 bonding electrons minus 2 antibonding electrons divided by 2. That's a bond order of 0. There's no energetic benefit for helium to form a diatomic versus staying isolated atoms. So helium doesn't form a diatomic. It's a noble gas that exists as single helium atoms in the atmosphere. Bond order of 1, stable system, forms a diatomic. Bond order of 0, unstable system does not. But helium cation, He2 plus, if you stripped an electron away, so you only have 3 electrons instead of 4, helium cation is theoretically stable. The bond order would now be 2 minus 1 over 1, which is a non-zero number. The bond order is 0.5. 2 of the electrons have dropped in energy, only 1 has risen in energy. So if they take a vote, 2 of the electrons want to form a diatomic molecule, only 1 electron doesn't want to form a diatomic molecule. Helium cation, dihelium cation, should be stable. You should be able to actually see dihelium as a cation. That's the simple case, the first row diatomics. It gets a little bit more complicated when you move down into the second and third row, because now we don't just have a 1s orbital. Within the same principal quantum number 2, we have both s and p orbitals. So there are more orbitals in the valence shell that have to be considered when we consider the overlap. The description of molecular orbitals in your organic text is not very good, but the first and second row diatomics are covered very well in your general chemistry textbook. I suggest you take a look at that chapter. It's in chapter 6. It's in chapter 10, I think, in Brown and Burston.